All right, so the chain rule. What is it? So suppose we want to differentiate a function that looks like this. You don't need to write down everything on this page. I'm just kind of introducing the concept here. But if we had a function that looks like that, the square root of x squared plus 1, right now we don't have a rule that will allow us to do that. But what we can notice is that f is what we call a composite function, meaning it's made up of multiple functions where one is plugged into the other. So if I let lowercase f be the square root of u, and I let u be x squared plus 1, then I can define capital F as the composition of the two functions, lowercase f and g, meaning capital F of x equals f of g of x. And we know how to differentiate both separately, so I could find the derivative of that. I could find the derivative of this. All right, so how do I find the derivative of the composite function? That's going to be it. So I'm going to give you a minute. This is important. It's in a blue box, so write it down. Write down the chain rule, and then I'll explain how it works. Give me a green check when you're finished writing it down. You're good to go, just so that I'm not talking while you're furiously trying to write. Let's go back to our last example from the previous slide where we had that function f of x equals the square root of x squared plus 1. What the chain rule says is that if you have a function that is made up of a composition of functions, which we do here, you can find the derivative by basically you take the derivative of the outermost function, keep the inside function the way it is, and then you multiply by the derivative of the inside function, okay? So this is a composite function. I'm going to rewrite it as x squared plus 1 to the half power. So just rewriting that square root as the 1/2 power. And if we think of it in terms of outside function and inside function, the outermost function is the 1/2 power, right? So the chain rule says, okay, first thing you want to do is take the derivative of that outside function. Well, to take the derivative of x to the 1/2 power, we would just use the power rule, right? So it would be 1/2 x to the negative 1/2. But notice that the chain rule is saying, but don't just plug in x, keep the inside function just intact. So whatever your original inside function was, we're going to leave it as is. What's our inside function in this case? Can you guys put it in the chat for me? Yeah, x squared plus 1. So we're going to leave x squared plus 1 alone for now. But then we multiply by the derivative of the inside function. So what would the derivative of x squared plus 1 be? So now we're looking for this, we're at this point, g prime of x. So yeah, derivative of x squared plus 1 is just 2x, and we're done. We've applied the chain rule. Now we can simplify that a little bit, but we've done the calculus to it, okay? The Leibniz notation is if I let y equal f of u and u equal g of x, then technically y equals f of g of x, right? So it's saying you take the derivative of the outside function with respect to u times the derivative of the inside function, which is u, with respect to x. All right, so let's derive this. You don't have to write this derivation down. I'm just going to do it. I just want you to participate in the chat. It's kind of a complicated one, but I think it's worth going through at least once so you know that it's not just a miracle that this works. We're not just making stuff up, right? This is mathematically proven material. So here's what I'm going to do. Let's see, I need to organize my page pretty well here. So I'm going to say capital F of x is equal to lowercase f of g of x, right? So capital F is a composite function, and I want to find f prime. So I can apply my limit definition of derivative to that. It's been a while. Hopefully you remember. That would be the limit as h goes to 0 of capital F of x plus h minus f of x over h, right? Now I'll put it in terms of the right-hand side of the equation for capital F, which would be f of g of x plus h minus f of g of x over h. Okay. Now I'm going to do a little setup. This is going to seem weird, but eventually we'll get there. So this is kind of a little aside. I'm going to define a new variable. Let's call it v. And it's going to be this. This is the way v is defined. Now, the one thing I want you to notice about the way I defined v there is what happens if I let h approach 0. What does this term become? What does that term become if I let h go to 0? Should look like a relatively familiar, not f prime, but yes, you're on the right track, Maisie, because that's not the function f, but g prime, right? That term will become g prime if I let h approach 0. Does that make sense? And so then what I would have is g prime minus g prime, right? Which is what? It's 0, right? So it's safe to say that if I let h go to 0, then v will approach 0. Okay? All right, I'm going to do another one. It's going to seem weird, but same idea. Let's call this one w. And it's going to be f of y plus k minus f of y over k. And I'm going to do minus f prime of y. Same logic there. I can say that if I let k go to 0, this whole term would then become f prime of y by definition, right? And so if that term becomes f prime of y, then w equals f prime of y times f prime of y. And that means w is going to approach 0 as well. Get out of here. All right. So now we've established that. Why have we established that? You have no idea, but as long as we can all agree that those statements are true, that's good enough for me. All right, so from this definition, I can do a little bit of manipulation here. I'm going to do it on the V equation. And what I want to do is I want to just isolate g of x plus h. I want to isolate that. I want to solve for g of x plus h. So that's going to involve, right, I'm going to have to multiply the h to the other side of the equation. And then I'm going to have to add g of x. And at that point, I will have isolated g of x plus h. And so what that'll come out to, I'm just going to do it all in one step, is that g of x plus h equals g of x plus the quantity g prime of x plus v times h. All right, and likewise, I'm going to isolate f of y plus k. So I'm going to multiply k to the other side, and then I'm going to add first thing I'm going to do is add over the f prime of y. Then I'm going to multiply by k. Then I'm going to add f of y. And that's going to give me this. F of y plus the quantity f prime of y plus w times k. All right. So now we're kind of ready to start trying to evaluate this guy. Okay? And the reason I can do that is I have an expression now for g of x plus h. I have an expression that I can replace this with, right? And that's this. Okay? So that's the first thing I'm going to do. So my limit, I'm coming back down here. And it becomes f of g of x plus h gets then replaced with g of x plus the quantity g prime of x plus v times h. Okay? That was just this term. All I did was replace g of x plus h with its equivalent. And now I'm going to subtract. Now I have minus f of g of x. And that's all over h. All right. So now we're going to get to the kind of confusing part, but stick with me. Now I want to be able to evaluate this. And the way I can do that is I have f of something plus something, right? Here I have a formula for how to expand f of something plus something, okay? So all we have to think about is that in this case, g of x is thought of as our y, and this whole term is thought of as our k. And then we can expand it using this formula. Just remembering that y is our g of x in this case, and then k is this whole mess, the g prime plus v times h, right? So then I'm going to expand it by using this formula. All right, so this says the way that that should expand is I should have f of y. So f of y, in our case, remember that y is g of x, so f of y would just be f of g of x plus, and then I have this portion to take care of, f prime of y. Sorry, give myself a little more room. So plus the quantity f prime of y, but in our case, our y is g of x, so that's going to be f prime of g of x, plus w, w is just w, times k. Now our k, remember, is all of this, so I'm going to multiply by all of that. So times g prime of x plus v times h. Great. And then I still have the minus f of g of x and that's still all over h. We're almost there. Now we're about ready to start simplifying. So notice that I have a positive f of g of x here and a negative f of g of x on this side, right? Come on, computer. There we go. Okay, so then all I have left is one term, all being multiplied together over h. Well, if you have h over h, we can divide out the h's, right? So now my limit becomes the limit as h approaches 0 of f prime of g of x plus w times g prime of x plus v. But we already referenced, what do w and v do as h goes to 0? Those are also going to approach 0. So as I apply that limit, w goes to 0, v goes to 0, and all I'm left with is f prime of g of x times g prime of x, which is our formula for chain rule. Okay? So you'll never have to recreate this proof, but I think it's important to go through at least once and understand, right? This isn't coming out of nowhere. We are able to derive these tools and then use them. The way I think of the chain rule is always derivative of the outside function times derivative of the inside function. All right, so let's practice a few of these. We already did this one, right? This was the first one. So anytime you're going to do calculus that with functions that involve radicals, the first thing you want to do is rewrite those radicals as exponents. Then identify the outside function. I really like to use the Leibniz operator here because it helps keep things organized. So if you don't want to do the derivative all in one step, you don't have to. You can do it like this. F prime of x equals, I'll do the derivative of the outside. And then I'll say, okay, times the derivative of the next function in. So times the derivative of x squared plus 1. So I've set it up to take the derivative. I just haven't actually taken the derivative of that piece yet. This is especially helpful when you have nested composite functions. So you're going to be dealing with sometimes functions that aren't just f of g of x. It could be f of g of h of k of x. And as long as you use this Leibniz operator, it'll help you organize and know that you're doing the calculus right. And then so I would take the next step and go, okay, so f prime of x is 1/2 times x squared plus 1 to the negative 1/2 times the derivative of x squared plus 1 is just 2x, right? And then we would simplify. This one can be simplified by noticing we have a 2 and a 1/2. So we can go f prime of x equals, then I can move that entire set of parentheses to the denominator to make the exponent positive. And if you wish, you can rewrite the exponent as a radical. So there you go. Okay, give me a green check when you're good with this slide and I'll move on. I'm going to skip this. We're just going to jump right into one. Okay, so first identify the outside function and the inside function. The outside function in this case is going to be your x to the power of 100, right? So derivative of the outside would be 100 times something to the 99th. What goes in those parentheses? What goes here? Yep. We keep it the same. Remember, it's f prime of g of x times the derivative of the inside function. Derivative of x cubed minus 1 is just 3x squared. Simplify this, I can just multiply the 3x squared to the front, so then I have 300 x squared times x cubed minus 1 to the 99th power. Okay. Give me a green check when you're good with that one. As always, if you have questions, please feel free to ask. All right, I'm going to move forward. So you can go back. I posted these slides. You can read that last slide. I'm just going to tell you verbally. We already kind of talked about this, but if you have multiple nested functions, you can still apply the chain rule. You just may have to apply it multiple times, okay? So here's where the Leibniz operator comes in extremely handy so that you don't confuse yourself. So I'm going to do f prime of x equals. Now we definitely have composite functions going on here. What's the outermost function? I agree, sine. So first thing we want to do using the chain rule is derivative of the outside function. What's the derivative of sine? Okay. So we're going to do cosine of what? Chain rule says derivative of the outside function. What are we supposed to do with the inside function once we've differentiated the outside function? Good, you keep it the same. So cosine of, and then we would leave this alone, right? Cosine of tangent of x. Now, at that point, we want to multiply. So I'm going to say times the derivative of the next function in. The next function in is what I underlined there in green, right? So derivative of cosine of tangent of x. So what I want you to focus on is you've dealt with this. The calculus on that piece has been done. You no longer need to do calculus with it. It just gets tagged along each line we move down, right? So now we're saying, okay, we need to take the derivative of cosine of tangent of x. All right, but that's a composite function as well, right? So we're going to have to use the chain rule on it. What's the outside function in that scenario? Good. What's the derivative of cosine? Negative sine. So what I'm going to have is this that we've already done calculus to times, now we're starting the chain rule again. So derivative of cosine is, so times negative sine of, what goes in those parentheses? Good, tangent. Because we're using the chain rule. So it's the derivative of the outside with the inside function left alone times the derivative of the inside function. So the inside function in that case is tangent. All right, so you can kind of see how that Leibniz operator is just sort of making its way through the chain, right? And now we're finally on the last piece of this, because we don't have a composite function anymore. You guys remember the derivative of tangent? We proved it last week. Good, secant squared. And so times the derivative of tangent is just secant squared. And I'm done. The only thing I did to simplify, I moved the negative, that's a -1, multiply, moved that to the front. And there we go. So we get negative cosine of tangent x times sine of tangent x times secant squared x. All right, questions, or give me a green check when you're good with that example. I think we got one more. So here, this is again, we actually have multiple layers of composite functions. What's the outermost function? What's the outermost operation that's happening? Yep, square root. So I'm going to make that a 1/2 power. Okay. So to take the derivative of this, we're going to use the chain rule. Take the derivative of the outermost function, which is just the power rule, right? All right, what gets left in the parentheses? Good, secant x cubed. Emily had that queued up for me. Oops. And I'm going to multiply by the derivative of that inside function, which is secant x cubed. All right, so we've done the calculus on that piece. That's just going to come as a multiplier every line below. But we still have a composite situation, right? We still have secant of x cubed is still a composite function. The outside function there is secant. Another weird one that we derived last week. Do you guys remember the derivative of secant, and or can you Google it very quickly to make it seem like you remembered it? Good. Secant tangent. Now, remember that chain rule dictates that we have to do derivative of the outside function, which in this case is secant tangent. But instead of just x's plugged in there, what are we going to have plugged in? Because chain rule derivative of the outside function, leave the inside function alone, right? And then you multiply by the derivative of the inside function. So what should go in those parentheses? Yeah, x cubed. And then I'm going to multiply by the derivative of the inside function. So by the derivative of x cubed. And that's going to be my last calculus, right? Because x cubed isn't a composite function. I can just use the power rule on it. So derivative of x cubed is just 3x squared. Derivative of x cubed is just 3x squared. All right, and the calculus has been done. We can do a little bit to clean this up if we like. What would I do if I were going to clean this up? I would probably rewrite this as 3x squared times secant x cubed times tangent x cubed over 2. That 2 is just from the 1/2, right? And then I would do root secant x cubed, and that comes from here. Oops. All right. That is it.